Okay. So this code, I'm just going to read in some Hubble data set. It's actually the data set I'm reading in here is a bigger data set than we considered on Wednesday. The data set that we had on Wednesday went out to a redshift that was about 0.1. That meant you could see about see backwards about 10% of the age of the universe. This data set goes out to a redshift that's near 1. So we can say all the way backwards to the first galaxies. So there's more data in this data set, and it has a greater reach back to the early universe. So I'm just going to read that in. And all I did in this code was I'm going to fit that data with the fitting function that we developed from Wednesday's class, so the one that we wrote, and then I'm going to fit it with the fitting function curve fit. So I'm just going to compare the results, check that, because they better agree, obviously. Okay, I'm sure I did this, but given that I'm an anxious person, I'll do it again. Okay, so this cell here, what am I doing here? All I'm doing is reading in the data, which is in a simple text file. This first line here was the data that you used last week, or we used last week, or maybe I used last week for Hubble data. And then this one here is this new text file that has many more it has 60 galaxies in it rather than 18 galaxies. It's the same sort of format, so it actually contains a column of redshifts. It contains a column of distances to galaxies, and it contains a column that is the uncertainties on the distances to the galaxies. In this bit of code, I'm just going to ignore the uncertainties and just work with the redshifts and the distances. I'm going to shut this. So I'm going to read this data in, and I'm going to strip out those first two columns that have my redshift, and it has the distance to the galaxies, and I'm just going to plot it so that we can see it. So the data from Wednesday's class are down here. If you remember, they went out to a redshift of 0.1, fractional redshift of 0.1. But you look at this data here, they go way out to the early universe, to the earliest galaxies. And so we're using this greater range of data here. Okay, so in this cell, and then in the next cell, I'm comparing the fit using the method that we developed in the last class and the method we've just been talking about with curve fit in this class. So I don't want to spend too much time on this cell because I just cut and paste what you've done from Wednesday's assignment and what I did in Wednesday's class. I just cut and paste that method of doing a least squares fit to the straight line. So here's that matrix M, which we need to calculate the best fit parameters. Here's the X is my independent variable, and then Y is my dependent variable. And if you remember, we calculate several matrices or vectors. Here the three of them are, based on the matrix M and the dependent variable Y. And then that's how we calculate the best fit parameters with this little line here. And so these are my best fit parameters. And if I run this, here's the fit to the data. So the data points are in red, they're the 60 galaxies, and then the blue line is my straight line fit to the data. So, you know, it sort of makes sense. I wrote out the slope and its uncertainty, and I wrote out the offset and its uncertainty here. And I also wrote out a chi-squared. So the chi-squared per degree of freedom divided by the number of degrees of freedom. That tells us the scatter of the data points about the best fit line. And I wrote these things out so we can quantitatively compare this this method, this is the homebrew method for doing the straight line fit, with the curve fit method. So look, you see that the slope is it's a little over 5,000, which kind of makes sense on this plot, right? This vertical axis here is a range of 5,000, and this horizontal axis is about 1. So we got a run of 1, and we got a rise of about 5,000. So that's the slope there. And you see the intercept is on this scale close to 0. It's approximately going through 0. That's what the offset says here. Okay, so that's all old stuff. So let's spend more time on this new cell here. So this is the cell in which I'm going to use curve fit. So let's just go through a few of the items in here. So the first thing is I've defined a user function, which is going to be used by curve fit. It's the first argument of curve fit, and it's the function we're going to fit to the data. And my function to fit the data is just a first order polynomial, so it's just a straight line. And so here I am expressing that function. Here's the offset, and here's the slope, and here's the dependent variable. So that's all I've done there. Then all I need to do is actually call curve fit. So let me just walk through these arguments of curve fit. So the first one, as I said, is the function that we're using. So I called it func, and so I'm just giving that name of that function. Then the next two are the independent variable and the dependent variable. We define those as X and Y when we read the data from the file. And then we could have included the uncertainties on the data points, but in our previous homebrew straight line fit, we assumed equal uncertainties. And so I'm just going to exclude the uncertainties from the data file here. And so it will just assume equal uncertainties. And so this is kind of the call to curve fit that should reproduce the calculation with our homebrew code. There's two items here that curve fit returns, and it's like what our homebrew returned. One was this vector of the best fit parameters. So pars is that vector. It just had 2-element vector. And then it returns the matrix that contains the uncertainties and the correlations. That's this covariance matrix here. Okay, so once I define this function and make this call, I'm going to get my best fit parameters and the uncertainties on those best fit parameters. I'm going to print them out like I did in the previous case. I'll print out the slope. I'll print out the offset. I'll print out the errors on the slope and the offset. And I'm also calculating the chi-squared here. I'll say a bit more about the chi-squared calculations in the next example. And then I'll just plot this data. And so here's our results. Magenta now is the data points, and in green now is the best fit to the data. And the slope is this 5,757 with some uncertainty on it. The offset, this minus 128.9. On this scale, it's close to 0. And the chi-squared, about 158,000. If we compare those upstairs here, you see we get very close to the same numbers. So, you know, the two methods are different. They're extremely close, but not exactly the same. One of them, we, as I say, solved at homebrew. We solved the problem analytically by analytically calculating the differentials with respect to the slope and the intercept. The curve fit function is done numerically, iteratively, by walking around in parameter space to find the minimum. So we shouldn't, there'll be some accuracy, some tolerance of the numerical iterative approach. But basically, we've ended up with the same results from the two methods. So I think that's telling us we coded our homebrew right, and we know how to use the curve fit right. So the idea of that code was just to prove to myself that I programmed the homebrew right, and I knew how to use curve fit, that they give consistent results. I think that was the only real purpose of that. Now I'm going to go on and use curve fit some more. We're going to look at some more details of least squares fitting, and some of the things that you would look at or check when you do least squares fitting to kind of validate your fit results, to understand your fit results. Things like, was the function a reasonable fit to the data? Or was the function not a reasonable fit to the data? Are there systematic differences between the data and the fit function, or are there not systematic differences between the fit function and the data? So we're going to kind of look at those sort of things. So in this code, I'm just going to use curve fit now. And actually what I'm going to do is something that we often do, and we'll do this in Wednesday's class as well. If you were planning an experiment, or if you're in astronomy, if you're planning some observations with a telescope or whatever, you would typically simulate your experiment ahead of time, and use the simulations to determine how well you can, measure the quantities you're interested in ahead of time. You have to do that. You have to do that because you've got to get time on the telescope. They go give you the time on the telescope. You've got to get funding for your experiment. You have to do it. So we are often in the business of simulating data, fitting the data to establish, how well or how poorly we can measure this or that quantity. And so I'm going to use, I'm going to simulate some Hubble data here, and then we're going to fit that Hubble data, and we're just going to look at the quality of the fits, basically. Okay, so in this first cell here, I'm just going to generate some fake data, some fake data of redshifts, fractional redshifts versus distance to galaxies, based on that data file, on that real data file. And so I'm going to, in this particular cell here, I'm going to imagine that I got 60 data points. So 60 galaxies. I've got the, this is an approximation for it, but I got the kind of roughly the measured expansion of the universe. So I'm taking that. I'm assuming that, nearby galaxies with this offset, they're not receding from me. So that's the offset here. And I picked some, this here is standard deviation. This is meant to be the sort of typical error of my measurements. And I'm going to generate a set of data based on this. So it's like I'm generating some fake, data on expansion of the universe and the redshift of the galaxies and the distance to the galaxies. So I'm going to assume a model, right, in which the basically the redshift is in proportion to the distance to the galaxy. So this little model here. So that's how I'm going to generate here's my dependent and independent variables. I'm going to add some noise to my measurements. So here I'm adding noise to the measurements of the distances to the galaxies. So like with any experiment, you're going to have some measurement noise, some experimental noise. And so I'm incorporating that in as uncertainties on my measurements of the dependent variable. So that simulating the data is in these 4 lines here. And then downstairs here, I'm just going to plot it out. And so here's my fake data on the expanding universe. Now it's a little different from the that real data. The real data had a bunch of points at low Z that were got from pulsating stars as standard candles, and it had some points at early in the universe that were actually got from using exploding stars as sort of standard candles to get that data. So the distribution is different. Okay, so we've made some data, and then I'm going to fit it, and we're going to look at the fit results, and we're also going to look at, first of all, we'll look at what we call the residuals, because when we fit data, you will often look at the residuals to check the quality of your fit, whether it's reasonable, unreasonable. Okay, so this is the cell in which I'm going to fit the data, and I'm going to plot the fit results, and I'm going to plot the residuals. So here, this is my function where I define the model that I'm going to fit to the data. So again, right now, I'm just going to assume a linear model. So there's the slope, this first parameter, and there's the offset, this parameter here. Now, you'll notice that I'm also building a list every time this function is going to get called, because I wanted to show you this kind of walk that curve fit will take from an initial guess to the best fit value. And so every time curve fit calls this function, I'm going to record where it is in parameter space. And I'm just going to accumulate the list of so curve fit's stepping through space to get to the minimum. I'm just going to record all those steps so we can look at what it did to get there, just to see how it actually worked, what was going on sort of under the hood. So that's all P1 array is. P2 array is just going to be a list of the slopes and the offsets as starting from the initial guess as curve fit works its way towards the minimum and chi-squared and the best fit values of those parameters. This is where I call the curve fit function. I'm calling it with the model. I'm calling it with the independent data points. I'm calling it this time. So this time I'm going to use the uncertainties on my data points. And so I'm passing those. There's a difference here. So with the function, the dependent and the independent and dependent variables, I don't need to, you always have to give those arguments. The uncertainty is a optional argument. So the way you include it is in this little statement here. So you have to say sigma. Sigma equals, and then you give your uncertainties. And this is where your question about the absolute sigma, this is where this is relevant. So you could put true or false here and it will take fractional or absolute errors. Okay. So this will return the best fit. And when I return the best fit, so I now want to describe, I'm going to look at the residuals and I'm going to look at the chi-squared. So I want to describe the calculation of those. So it returns this a vector called pars, which in this case has two elements, which are the slope and the intercept. So I can calculate the best fit curve through the data, and I've called that y fit, by extracting from this array the best fit slope and the best fit offset. And then for each data point, xi, I calculate the value of the fit function. So this really defines the fit function itself. Once I got the fit function, I can calculate the residuals, which are the difference between the fit function and the data points. Now, sometimes you'll calculate the residuals where they're kind of absolute residuals. Here I've calculated sort of fractional residuals. The residuals with respect to the uncertainty on the data points. That way you can look at the residuals and say, well, look, 2/3 of the residuals should be less within the range plus or minus 1. It should be unlikely to get residuals that, at 3 plus either greater than 3 or less than minus 3. So you can sort of use your understanding of the standard deviation. And so that's why I normalized them here. With the residuals, you can then calculate the chi-squared is nothing other than the sum of the squares of the residuals. And if I divide it by the number of degrees of freedom, which is the number of data points less the number of parameters in the fit, that chi-squared is a good test of the quality of the fit. So if that normalized chi-squared, the chi-squared per degree of freedom, it should be about 1. It should be about 1 within a precision of 1 over the square root of the number of degrees of freedom. Okay, so that's all I did. Let's execute this cell. I won't go into bore us all with all the details of the plotting functions I called. I just jump down here. Okay, so this here, unfortunately you can't see it very clearly, but this is the data, and there's a line through here. I could make it more clear if I did. So the magenta points are the data, my simulated data, and the green line is my fit to my data. And you see that obviously that by eye, it looks like the fit is going through these data. This graph in the middle here. So this is rather than the data points versus plotting the data points versus the independent variable. Here I'm plotting the residuals as a function of the independent variable. So there's 60 points here too, but these are the differences between the fit function and the simulated data. The way I did it was it's actually it's the fit function minus the data. So you see this first point is negative. That's because the fit function is below the data point. So I've taken the fit function less the data point, so I'm getting a negative number. If you see here, this is where the data point is below the fit function. So this is going to give a positive value for the residuals. So here you see the scatter of the residuals. And again, I've normalized this, so it's the it's the scatter of the residuals in units of the uncertainty on the data points. So what you would typically look at the residuals for is just a sort of a better by eye test than looking at the data itself, is the scatter consistent with the uncertainties that we have on the data points? And it looks like it is. So we would expect 2/3 of the data to be within plus or minus 1 sigma, and it looks roughly right. We'd also look at it, do the residuals show any trend, say from the left bookend to the right bookend of the plot of the residuals? Do they show any trend that is kind of a systematic deviation between the fit function and the data themselves? And I don't see any trend here. It just seems to be a general scatter. So this shows like the fit was a reasonable fit to the data. And of course, we generate the data from a straight line and we fit it to a straight line. So it should be a reasonable fit to the data. This is another plot that we would often make. So this is really just a histogram where I've plotted horizontally in this histogram is actually the values of the residuals, and vertically is the number of times I've got those residuals. So if the this bin here corresponds to a bin where the residuals are basically 0. This bin over here is where the residuals are positive 1 sigma. This bin over here is where they're negative 1 sigma. This bin would be a residual that's 2 sigma. This bin down here would be a residual that's minus 2 sigma. And so you see this +2 is probably this data point up here. And this -2 is probably this data point right here, or maybe this one. You see there's a few more in the negative direction that are large sigmas. So it's probably these. There's less of them here. So it's just another way of plotting the distribution. Rather than plotting each individual residual, I've made a histogram out of those residuals that tells you how far they're away from the data is from the fit function. Okay, so the next plot that I wanted to show you, which more has to do with how the curve fit function works, is I just wanted to show you chi-squared distribution in the parameter space. So remember, the way think about chi-squared is it lives in this parameter space, in this case, the slope parameter and the offset parameter. It's sort of a contour in that space where we're trying to find the valley. So on this, in this cell, I've just made a plot of chi-squared in that space. And I'm not going to go into you can take a look at the details of the code, but I just really want to show you the plot. And then I'm going to show you the path that the curve fit program took to get from a guess, the initial guesses for the parameters, to the actual values of the parameters. So that's these two plots here. So let's look at this upper plot here. So horizontally is the slope parameter, and vertically is the offset parameter. Remember, we our truth value for the slope when we simulated the data was 5,000, and our truth value for the offset was 0. So the truth values is somewhere around here. But then when we generated the data, right, we introduced statistical noise, experimental noise. So, you know, the best fit values of the slope and the offset not necessarily going to be 0 and 5,000. They're going to have some noise on them too. These contours are contours of chi-squared. So everywhere on this oval here, or this ellipse here, is the same value of the chi-squared. every value on this bigger ellipse here, which loops around over here, is the same value of the chi-squared, and so on and so forth. So you're seeing the value of chi-squared here. The best fit chi-squared is right at the bottom of the valley here. And then you're seeing the walls or the mountains on either side of that best fit value of the chi-squared. And so this is what chi-squared looks like. And so this is the space in which curve fit steps around. It steps around in this space trying to find the minimum. And that's where the best fit parameters are. It's actually interesting that with just two parameters, I think there are some tricks in curve fit under the hood that gets it to the minimum very, very quickly. This analogy of tiny steps trying to get down the mountain isn't quite right. It would be more right if you had a large parameter space, many parameters in your fit, and it has to walk around in small little steps working its way down. But in this lower fit here, in this lower panel, lower figure, these are actually, these magenta points are the steps that curve fit took to iteratively get from a guess, which was just zeros for the parameters, down to the best fit values, which are a little under 5,000 and close to zero. So it took these massive, on the scale of the top plot, massive steps through this parameter space to end up at the best fit values. So that's just showing you under the hood how the curve fit program works. Okay. The next thing I wanted to show you was, so I said that typically if you want to get time on a telescope or you want to build an experiment, you've got to simulate your experiment and find out how well you can do your experiment. We wouldn't just simulate it once. Right? We would simulate it hundreds, thousands of times, often under the different conditions to optimize the experiment or optimize the observation time. All I've done here is I've run this simulation 1,000 times. And I've run it 1,000 times so that I can collect, as if I've done 1,000 experiments or 1,000 observations, collect 1,000 results and look at the scatter in those results and check that I understand the scatter in the extracted values of the slope and scatter in the extracted values of the offset. Typically, if you're planning an experiment, planning an observation, you're worried about, well, is there systematics that might pull your interesting observable or your interesting measured quantity in one direction or another direction? You'd be interested in exploring systematic effects like this. Anyway, again, I'm not going to go into the details of this cell, but basically all I'm doing, I've got a loop now over a range of 1,000. And this is 1,000 fits to 1,000 experiments. And so I generate in this loop now a simulated data set 1,000 times. I fit the simulated data sets 1,000 times. And then downstairs here, I'm going to store the slope that I extract every time I do the fit. I'm going to store the offset every time I do the fit. And I'm going to store the chi-squared every time I do the fit. So I'm going to just store those quantities that are sort of the results of the fit, the best fit parameters in the chi-squared. So that's all that happened here. Okay, so then we're going to look at all this. So now I've got 1,000 chi-squareds from 1,000 simulations of the experiment. I've got 1,000 slopes, 1,000 offsets from the 1,000 simulated experiments I do. Let's look at the chi-squareds. So that's what I'm going to do in this cell. Again, I'm just going to jump to the plots. So the upper plot here is the this horizontal axis is just an index for the experiment, the simulated experiment. It's just going to run from 1 to 1,000, or the index for the 1,000 fits, 1 to 1,000, and then I'm just plotting vertically the chi-squared. And so here you see the chi-squareds are distributed around 1, so they should be distributed around 1. They have a scatter around 1. That scatter should be the scale of 1 over the square root of the number of degrees of freedom. So we got 60 data points. We got 2 parameters, so that's 58 degrees of freedom. So square root of 58 is between 7 and 8. And so the scatter should be just a little under 10% of 1, something like that, a little over 10%. So 1/7, somewhere between 1/7 and 1/8. And that looks about right if you look at this data right here. It's probably a little clearer if instead of plotting the 1,000 chi-squareds as 1,000 points here, in this lower panel, I made a histogram earlier on. I made a histogram here. So for each value of the chi-squared, if you get that chi-squared, I increment a bin of this chi-squared histogram. So you see here, this bin that's close to 1, this has 100 chi-squareds I got that were corresponding, sat inside this bin, between the lower and the upper edge of this bin. There was one case over here where I got a chi-squared that was nearly 1.7. There's a couple of cases down here where I got chi-squareds of 0.5. But what you're seeing here is just the chi-squared distribution. And you're saying that roughly the width of it should be a little over 10%, maybe between 10 and 15%, plus or minus 10 or 15%. And it looks about right. So that's the chi-squared distribution. Then I'm just going to do the same sort of thing for the fit parameters. So again, I won't go through the details of making the plots, but I have an array of 1,000 slopes. And so again, the top panel here is the 1,000 experiments that I did, or the 1,000 simulated experiments. The vertical axis is, I'm not simply plotting the value of the slope. This time I plotted the value of the fitted value for the slope. So the best fit value of the slope less the truth value of the slope. In my model, I used a slope of 5,000. So whatever value I fitted the slope to, I subtracted off that truth value. So there I'm really seeing the statistical noise that I've injected into the data. So you see that when I do the fitted slope minus the truth, then those values are distributed around 0, which they should be. I'm not going to always get 0 because I've got statistical noise, but it should be on average distributed around 0. And the width of the range of the distribution should be a reflection of the error, the uncertainty on the extracted slope. And so you see here in this bottom panel, I kind of made a histogram of this data again. So now if you got values of fitted slope minus true slope that are 0, it would be in this bin here. So there's a lot of data in this bin here. Occasionally you get a fitted slope that is much minus the truth, that is quite away from 0 on the positive side, or quite away from 0 on the negative side. So these are these points upstairs here. these points downstairs here. But this is the distribution of the fit results. And this should be consistent with the errors that the fit is giving you on the individual slopes. And then just to end up with here, I think, this is the same thing for the offset. So the same pair of plots, top one, the 1,000 simulated experiments. This is the offset fitted value minus the true value. It should be centered around 0, it is. It should have noise in it that reflects the experimental noise that we injected into the data. And then again, here I made a histogram out of that. So values close to 0 are in this bin here. And then you see occasionally we get values that are much bigger, up to about 50, much smaller, down to about minus 50 for the difference between the truth and the fitted value. So that's just kind of a tour through the sort of things that you might look at when you fit data. You might look at residuals, you might look at chi-squareds, and the sort of things that you might look at when you're planning an observation or planning experiment. You would often simulate your experiment many times and look for systematic effects, systematic distortions in the parameters that you extract from your simulation of the experiment. So we looked in the slope, we looked in the offset, we looked at the chi-squared distributions for those sort of systematic effects.